Okay, now in this video we want to look at power functions. That is x to the power of n, where n could be any, well, technically it could be any number, but we're talking about any rational number. So whole number, fraction, yeah. So we want to look at the different kind of shapes that we can get for power functions depending on the value of n. Okay, and I want to be clear about the fact that there's a wide variety of graph shapes and things that we can get here. The purpose of this video is not for you to rote learn and remember every single graph shape and how they all correspond to everything, and you know there's a lot of information here. But it's to sort of help you talk through and rationalize your way through the different types and the different shapes and why they're going to be those different shapes and how they connect to the shapes that we already know. And therefore, if we are faced with a graph of, y equals x to the power of 2/3, that we should be able to think through what that shape would look like. Okay, I'm not suggesting you should be able to just pull it out of your memory and know exactly what it looks like straight away, but that you should be able to think it through. Okay, so let's work our way through the different variations. So we're just looking at x to the power of n. Obviously then once we've got the basic shape of x to the power of n, we can then dilate it, reflect it, translate it using our transformations. But being able to establish the basic shape is important. Okay, so let's start with the simplest things. X to the n, where n is a positive integer. So if n is an even positive integer, that is x squared, x to the power of 4, x to the power of 6, x to the power of 8, 10, 12, etc., we're going to get a family of functions that we're quite comfortable with. So y equals x squared we know is the parabola. Y equals x to the power of 4 is the blue graph, which is a more extreme parabola. Okay, so what's important here is that all of these shapes, no matter what that power is, they're all going to go through the point 1, 1. Okay, when x is bigger than 1, as we make the power bigger, the y value is going to get bigger. So that's why the x to the power of 4 graph sits higher up and is steeper than the x squared graph. Okay, the same is true when x is less than negative 1. Okay, it's a mirror image. X to the power of negative, sorry, not x to the power of negative, negative 2 to the power of an even number is the same as positive 2 to the power of an even number. So we get that symmetry. And it's bigger than negative, so negative 2 to the power of 4 would be bigger than negative 2 to the power of 2. So that's why the blue graph is taller than the red graph outside of negative 1 and positive 1. Okay. However, between 0 and 1, so when we have fractional x values, if you increase the power, so if you have half squared, which is 1/4, but if you have half to the power of 4, you get 1 on 16. So the bigger the power, the smaller the value, if the x value is a fraction. So hence why our quartic graph sits below the parabola between 0 and 1, and obviously the same thing happening between 0 and negative 1. And then that just gets more extreme. So x to the power of 6 is steeper than x to the power of 4 outside of 1 and negative 1, okay? And it is closer to the x-axis between negative 1 and 1, okay? X to the power of 8 would just be an even more extreme version. Steeper here, closer to the x-axis here. X to the power of 100 would be even more extreme, okay? So we've got the sense of what is happening in that family. The odd powers, okay? X to the power of 1 obviously is the simplest one, but that's just a linear graph. We're not really getting this shape. So let's start with x cubed as being the simplest odd power. So x cubed we know is this traditional cubic with a point of inflection. It goes through -1, -1, and 1, 1. And then as we increase the power, we see the same sorts of things happening as we did with the even functions. X to the power of 5 is going to make numbers bigger than 1 get even bigger than x cubed, for example, whereas x to the power of 5 is going to make numbers less than -1 get even more negative quicker than x cubed. So what I mean by that is if you had, negative 2 to the power of 3, which would be -8, versus negative 2 to the power of 5, which would be -32. So the power of 5 graph is going to be lower down when we're talking about negative numbers back here. Okay. And then similar to what we saw with the even powers, if we've got a fraction to the power of a bigger power, it gets smaller. So the graphs get closer to the x-axis between 0 and 1, okay? So we can see x to the 3, x to the 5, x to the 7. We would expect the x to the 9 would be steeper here. It would go through 1, 1. It would get close to the x-axis quicker here, okay? And then it would go through -1, -1, and it would be steeper down here. And that would only continue as we increase those odd powers of x. Okay, some properties of these functions. If n is an even power, then we have an even function. It's symmetric about the y-axis. You can go back and have a look at the video on odd and even functions, probably 3 videos ago maybe. Whereas if n is odd, we get an odd function, a function that when we reflect it in the x-axis, we get the same thing as if we reflect it in the y-axis. The even function goes through 0, 0, 1, 1, -1, 1, all of them, no matter what the power of n. The odd functions go through 0, 0, 1, 1, -1, -1. The odd-powered functions are one-to-one functions. The even-powered functions are many-to-one functions, so not one-to-one. So therefore, in finding inverses, they would need to be inverse functions. They would need to be restricted. For the even functions, as x approaches positive infinity, so as x gets bigger, the function also gets bigger, okay? As x approaches negative infinity, the function also gets bigger. So as x approaches plus or minus infinity, f of x approaches infinity. Whereas for odd functions, as x approaches infinity, the function approaches infinity, but as x approaches negative infinity, the function approaches negative infinity. Maximal domain of an even-powered, a power function with an even power is R, and its range is from 0 to infinity, inclusive of 0, whereas the odd function's maximal domain is R and range is R. So we've already thought about functions of this form in the polynomials topic much earlier on, and so these should be pretty familiar shapes, as should applying transformations to these shapes. So that's the simplest power function. Then let's think about x to the power of n, where n is a negative integer. Okay, so remember x to the power of a negative, x to a negative power is 1 on x to that power. So if we're looking at x to the power of -2, that's 1 on x squared, which we know is a truncus. Okay, and again, once we've got our truncus shape, the other negative even powers are just more extreme versions of that truncus shape. So they all go through 1, 1 and -1, 1. But we can see if we have 1 on x to the power of 4, when the x is bigger than 1, we've got x to the power of 4 is bigger than x to the power of 2. Okay, so for example, we would have 1 on 2, so let's say when x is 2. 1 on 2 squared would be 1 on 4, whereas when x is 2, this is 1 on 2 to the power of 4, which is 1 on 16. So the blue graph is lower down than the red graph, i.e. the 1 on x to the 4 is lower down than 1 on x squared at x equals 2. And that only continues to happen as the x values get bigger. The blue graph will always remain below the red graph, so it's approaching the x-axis more quickly. Whereas if we have a fraction, so if we were to look at when x equals a half, for example, okay, this would be 1 on 1/2 squared, which is 1 on 1/4, which is 4, whereas this one would be 1 on 1/2 to the power of 4, which is 1 on 1/16, sorry, not 1 on 16, 1 on 1/16, which is 16. So the blue graph gets bigger much more quickly when we're dealing with, we have fractional values. Okay, clearly undefined when x equals 0, so we have that asymptote at x equals 0. Same logic here between 0 and -1. We've got fractional values on the denominator, so when we square them, when we raise them to a larger power, they get smaller, and hence when we're dividing by that smaller value, it gets bigger. And same logic as to what happened out here as to what happens down here. The blue graph will approach the x-axis more quickly. So we've got here pictured 1 on x squared, 1 on x to the 4, 1 on x to the 6. If we were to add in 1 on x to the 8, it would be steeper here. It would go through -1, 1, sorry, but it would be closer to the x-axis here. Okay, same logic over this side. It would be steeper here, it would go through 1, 1, but get closer to the x-axis quicker. Obviously, it's hard to show what's happening out here, where things are all pretty tight. If n is an odd function, the most basic function we're dealing with here is 1 on x to the power of 1, so the hyperbola. And then the next versions of that are just more, again, more extreme versions of that. So for big values of x, for values of x bigger than 1, the bigger the power on the denominator, the smaller the value will be. And so the graphs get close to the x-axis more quickly, whereas when we're between 0 and 1, the bigger the power on the denominator, the smaller the denominator is, and therefore the bigger the entire value is. Okay, so again, if we were to add in x, the next one, x to the power of 7, it would be even steeper here. It would also go through 1, 1, and it would get close to the x-axis more quickly here. Okay, and the same happening over here. Steeper here, go through -1, -1, and closer to the x-axis here. And we can continue that for x to the power of 9, 11, 13, etc., etc. Properties, the even powered function, so one on x to the power of an even number, are even functions. The odd ones, one on x to the power of an odd number, are odd functions. Both have asymptotes at y equals 0 and x equals 0. The even powers would be go through 1, 1 and -1, 1, whereas the odds would go through 1, 1 and -1, -1. The even-powered functions, as x approaches positive infinity and negative infinity, the function is approaching 0. Okay, we could probably add in here, you know, as x approaches 0, the function approaches infinity. Okay, which is all about our asymptote at x equals 0. Okay. For the odd ones, as x approaches plus and minus infinity, the function also approaches 0. But interestingly, technically, we have as x approaches positive infinity, f of x approaches 0 from above, so from higher x values, whereas x approaches negative infinity, f of x approaches 0 from below, so from underneath. Okay, so technically we would write that way. Again, we've also got different things as x approaches 0 from above, so from this direction, the function approaches positive infinity, whereas as x approaches 0 from below, so from this direction, f of x approaches negative infinity. Okay. Domain for the even-powered functions is r excluding 0, same for the odd ones. However, range for the even ones is r plus, because the whole graph sits above the x-axis. Given that we're squaring and raising the power of 4, we don't get negative y values, whereas for the odd ones, the range is all real numbers excluding 0. Okay, so let's then think about power functions with fractional powers. So simple fractional powers, i.e. one on a number. Okay, so we could think about those as being, remember, x to the power of 1 on n is the nth root of x. Okay. We can also think about x to the power of 1 on n as being the inverse of x to the power of n. So if n is an even number, okay, let's think about the most basic one. X squared looks like this. In order for it to have an inverse that exists, we have to have it 1 to 1, so it's just going to be half of it, by default the positive half, and then the inverse would be x to the power of a half, which we know is the square root of x. If our original function is x cubed, okay, the inverse of that is x to the power of a third, so mirroring this in the line y equals x, we get this sideways cubic graph. Okay, no need to restrict that because the cubic is 1 to 1, so its inverse is also a function. If n is an even negative value, so x to the power of -1/2 is what we want to think about, but we want to think about that as being the inverse of x to the power of -2. So x to the power of -2, remember, is 1 on x squared, so that's the truncus, okay? And its inverse is going to be a similar kind of shape, just with, you know, slightly different shaping. And it's pretty much the same happening for the odd-powered functions. So, for example, we could have gone with, so 1 on, x to the power of -3, we know is like the hyperbola. Now, given that the hyperbola is 1 to 1, there's no need to restrict it, whereas the truncus technically is both of those things, but we have to make it 1 to 1 before we find the inverse, and so hence we only get one branch to the inverse function, whereas with the odd powers, x to the -3 is the full hyperbola shape, and so its inverse is a similar sort of thing, meaning we'll get both branches of that. Okay, Alright, so those are the four basic shapes. So now let's look at more generally, families of these ones. So x to the power of a quarter, to the power of a sixth, to the power of 8. These ones, x to the power of a fifth, a seventh, a ninth. X to the power of negative a quarter, negative a sixth, negative 8. X to the power of negative 1/5, negative 1/7, etc., etc. So let's extend out those families. So let's start with this, where n is, we've got fractional powers, x to the 1 on n, where n is a positive even value. Okay, so that's this one here, 1 on n, where n is a positive integer. If it's even, we know that this was x to the power of a half. And then again, if we look at adjusting that denominator, so x to the power of a quarter versus x to the power of a sixth, again, if we have x values bigger than 1, okay, a power of a quarter is going to make it more small than a power of a half. Remember, this is square rooting, and this is taking the fourth root. So these are definitely going to be smaller values if we have a number bigger than 1. However, if we have a number between 0 and 1, the fourth root of, let's use 16 for example. So let's say we're going to have the fourth root of 16, well that's 2, as opposed to this one where we have the square root of 16, well that's 4. So this red graph for a fractional value, sorry, because we're looking at, the red graph should be, sorry, I'm only making my point, I don't want to look at 16, do I? I want to look at 1/16, we're looking at fractions. So if it's 1/16, then this would be a half, whereas if this is the square root of 1/16, we get a quarter. Okay, so what I'm looking at here is between 0 and 1, the red graph should sit lower down than the blue graph. A quarter is smaller than a half. Okay, and that would be even more exacerbated by a 1/6. If we were able to take the sixth root of 1/16, sorry, it would be something that is bigger than a half again. So again, if we were to look at adding in x to the power of 1/8, it'd be getting bigger here. It's not going to ever exceed 1, but it's going to get closer to 1 there. It'd go through 1 there, and it's going to get big, but less quickly out here. Okay, and we would have more and more extreme versions of that. Odd powers is the sideways cubic. Again, sort of getting more and more extreme. So this is x to the power of a third, a fifth, a seventh. If we looked at a ninth, it would be more flat here. It would go through -1, -1, and it would be further away from the x-axis here. Point of inflection there still, further away from the x-axis here, but after 1, 1, closer to the x-axis. Okay, again, more and more extreme. But that sideways cubic, that idea that if you know what x to the power of 3 looks like, you can work out what x to the power of a third looks like. If you know what x to the power of 9 looks like, which is just an extreme cubic, then you know what x to the power of a ninth looks like, an extreme sideways cubic. Okay. These, even looking in this column first of all, they're neither odd nor even, not symmetric about the y-axis. We also don't get the same thing if we reflect in both the x and the y-axis. So neither odd nor even. Goes through 0, 0 and 1, 1, every single function in the family. As x approaches infinity, f of x also approaches infinity. It's just going to get there a lot more slowly on this path than it does on this path, but it's still getting bigger and bigger and bigger. Maximal domain is 0 to infinity including 0, and the range is also 0 to infinity including 0. For the odd denominator powers, these are odd functions. If you reflect in the x-axis, you get the same thing as if you had reflected in the y-axis. Okay, so odd functions, they all go through 0, 0, 1, 1, and -1, 1. As x approaches infinity, f of x approaches infinity, albeit quite slowly. As x approaches negative infinity, f of x also approaches negative infinity, albeit quite slowly. Maximal domain here is R, and the range is also R. Okay, and then finally we look at the fractional powers where n is a negative integer. So x to the power of 1 on a negative value. Okay, so remember we looked at these basic shapes up here. If we know what it's essentially, it's the inverse of the truncus, so we're only going to have half of it because we have to make it 1 to 1 before we find the inverse. This is the inverse of a hyperbola shape, and we're going to have 2 branches because it already is a 1 to 1 function. So, let's go back to those negative integers. So we've got these sort of reflected in y equals x half of a truncus shapes. Again, getting more and more extreme as you make that denominator bigger. So still going to be closer to the y-axis there, going to be closer to y equals 1 there, going to go through 1, 1 there, and then going to be, again, closer to y equals 1. So it's all sort of getting closer and closer and closer to that value there. The odd denominator ones, again, they're sort of the reflected hyperbolas, okay? So hyperbola going more this way, so reflected hyperbolas. So we've got both branches of them. Again, increasing the power, increasing the size of the denominator of that power is only going to result in a more extreme version, closer to y equals 1 there, through 1, 1 there, and closer to y equals 1 from below down there. Again, we can talk about properties. These even ones are neither odd nor even functions. We have asymptotes at y equals 0 and x equals 0. They all go through the point 1, 1. As x approaches infinity, f of x is approaching 0, quite slowly for some of them, but it will eventually get towards 0 as we head on further out. Okay. As x approaches 0, f of x is approaching infinity, so that's our vertical asymptote at the y-axis. The maximal domain is R+, so it doesn't include 0 because of the asymptote. The range is also R+. For the odd ones, we have odd functions once again. If you mirror in, if you mirror in the x-axis, you get the same thing as if you mirror in the y-axis, okay? So these are, I wrote those wrong. Mirror in the x-axis, you get the same thing as if you mirror in the y-axis. So these are odd functions. Asymptotes have equations x equals 0 and y equals 0. All of these functions go through 1, 1 and negative 1, negative 1. As x gets really big, f of x approaches 0. Okay, it's going to do that more and more slowly, but it will eventually get towards 0. As x approaches negative infinity, it also approaches 0. Technically, we'd say this f of x approaches 0 from above here and approaches 0 from below down here. Maximal domain is R excluding 0, and the range is also R excluding 0. Okay, so those are us just thinking through the different kinds of things we could happen. The powers could be integers, positive or negative. The powers could be fractions with positive or negative denominators, and all of the different combinations of those things to think through. So as I said, I'm not expecting that you memorize all these facts. It's not at all the goal, but I want you to be able to kind of think through, right, if I have to think about the graph of y equals x to the power 1/7, what is that going to look like? Well, I know x to the power of 7 is a sort of more extreme x cubed, okay, and the inverse of that, therefore, is a more extreme sideways cubic, you know. If I've got x to the power of negative 1/2, well, that's the inverse of x to the negative 2, which is a truncus, so it's sort of going to be something truncusy like as well. So you want to be able to think through what the graph would look like on the basis of your knowledge of these functions. Okay, so let's have a look at a couple of examples here, because then we can sort of also combine those things together a little bit. So here we've got the graph of x to the power of 1/3 pictured below, and using this to help us, we want to then sketch the graphs of x to the power of 2/3, x to the power of 4/3, and x to the power of 5/3. Okay, so let's think first of all about x to the power of 2/3. So I'm going to think about this as being x to the power of 1/3 squared. So essentially, I'm taking all of the y values on this 1/3 graph and squaring them. Okay, so let's start with the key point here. So this is 1, 1. If I square the y value, so what we're saying here is 1 to the power of 1/3 has a y value of 1, so that's 1, and then 1 squared will be the y value for the new function. Okay, so 1 squared is still 1, so it's also going to go through 1. Now, as we move out here, we have y values that are bigger than 1. If you take a y value that's bigger than 1 and square it, it gets bigger. So the graph's going to be higher up out here, and it's going to get bigger at a bigger rate. So this number squared will be bigger than this number squared, for example, okay? And that will continue. However, when we're talking about fractions, okay, if we've got, for example, let me think about a number that might work. If I think about when x equals 1/8, okay, so 1/8 to the power of 1/3 is a half, and then if I do that, sorry, I wrote 3, sorry. So if we have 1/8 to the power of 1/3, that is cube root of 1 and cube root of 8, so that's half. And then if we square that, we're going to have a quarter. Okay, so a third, the graph of x to the power of a third, the red graph goes through the point 1/8, 1/2, that's about there, but the squared graph is going to go through 1/8, 1/4, which will be lower down. Okay, so the fractional values are going to get smaller when we square them. The numbers bigger than 1 are going to get bigger when we square them, and so we're going to get a graph that does something like that. Okay. Now, if we think about x to the power of 4/3, okay, so y equals x to the power of 4/3, I'm going to think about that as x to the power of a third to the power of 4. So it's going to be more extreme, okay, so it's still going to go through 1, 1. Compared to the 2/3 power, it's going to get bigger more quickly, because raising a number bigger than 1 to a power of 4, it results in a bigger answer than a power of 2, okay. Now, I'm not worried about scale here, I'm just trying to get shape. Now, the other key thing to notice is that 4/3 is bigger than 1, whereas 2/3 is smaller than 1, okay? So if you just had x to the power of 1, that would be the straight line, okay? So if you're going to have x to the power of a number smaller than 1, when you're talking about the fractional value, so when I'm looking at in here, it gets bigger. Whereas if it is x to the power of a number bigger than 1, it's going to get smaller. For example, what I mean by that is if you have 1/4 to the power of a half, okay, it's the square root of a quarter, that becomes a half, so it got bigger. Quarter went to being a half. Whereas if you have 1/4 to the power of 3/2, okay, so that's a number that's bigger than 1, okay, it's 2 powers in 1, you square root it and then you cube it, it's going to be 1/8. So that gets smaller and that gets bigger. So if the power is bigger than 1, the number is going to be smaller. So what happens is, bigger than 1 it gets bigger, so the graph will sit, so that's why the power being less than 1, the value got bigger. Okay, so here, the blue graph where the power was less than 1, I'm just talking about in the fractional sections, the value got bigger, okay? So it is, bigger than the line y equals x, bigger than the power of 1, okay? Bigger than if we just had it to the power of 1, okay? Whereas when we use a power that is bigger than 1, and we're talking about a fractional value to a power bigger than 1, it is going to get, it is going to get smaller. So not only, it's still going to be smaller than the red graph, but it's not going to take this shape is what I'm talking about. It's now going to bend under the line y equals x. So it's actually going to go this way. And actually the same thing happens here. It should get bigger than the line y equals x. Okay? So this should be x to the power of 4/3. Okay? Because your power of 1, x to the power of 1 should be somewhere between x to the power of 2/3 and x to the power of 4/3. Okay, so it's actually going to curve around the other way. Now, then the last one we want to have a look at is x to the power of 5/3. So again, if we're looking at, let's change colour again. If we've got y equals x to the power of 5/3, I'm going to think about that as x to the power of a third to the power of 5. Now, the other thing I didn't talk about is in these first two graphs, the blue and the green graphs, I didn't draw anything back here. And that's because, and that was my mistake. So when we take I've really confused you here, haven't you? Let's go back to the blue graph. We focused on the right-hand side of the blue graph and we got that right. Now, if we think about what's happening down here, if we take all of these values and we square them, so let's take that point, for example, that's at -1, -1. If we're going to square its y value, it's going to come up here to -1, +1, okay? Here, if we're going to square its y value, we're going to get the same thing as, we're going to get the mirror image of what happened over there. So we're going to get that sort of thing happening. So it should be the mirror image of the blue graph. Okay, I'll try and get it symmetric. I had it finishing up there. Okay, so it's actually going to be this sort of seagull shape. When we have the when we did to the power of 4, which was the green graph, Okay, we've focused on getting it right on the right-hand side of the y-axis, but because it's power of 4, we're going to have the same thing over here. So again, we think about this point at negative 1, 1, it's going to come up to negative 1, negative 1 is going to come up to negative 1, 1, when we then raise it to a power of 4, because it's an even power. And we're going to have the mirror image of this graph heading up here. Okay. Now, the difference with the 5/3 is when we take the graph of a third and raise it to a power of 5, okay, it's going to get, when x is bigger than 0, it's going to get more extreme than the green graph. Should definitely be higher up than, it should relative to y equals x, it's going to be lower down for fractional values and higher up for values bigger than 1. But the difference here is it's not going to be symmetric in the y-axis. It's not going to be over here as well, because a negative number to the power of a third and then to the power of 5 is still going to be negative. Okay, so we're going to be seeing it mirroring down there. Okay, so it's going to be more like a cubic kind of graph. So I'm not expecting you to be able to take this and immediately draw this shape, but I want you to be able to think through, okay, what would x to the third look like, and therefore what would x to the 5/3 look like? Let's verify those graph shapes with our CAS, just because I've confused you slightly, I think. So x to the power of a third is that one there. If we then look at x to the power of 2/3, okay, we should get that lower down when x is less than 1, higher up when x is bigger than 1, and symmetric about the y-axis because of the even power, okay, because we're essentially squaring everything. All right. Then if we have a look at x to the power of 4/3, we see that curvature change, because that's because we've now gone from being a power less than 1 to a power bigger than 1. So relative to the line y equals x to the power of 1, we should be seeing quite a change. Okay, so we've got that shape there. Again, the even numerator is making sure that we're taking an even power of everything, and so everything should be above the x-axis, and we should have that nice symmetry about the y-axis. Whereas if we have a look at x to the power of 5/3, we see that we get the bit down here as well. Okay, you'll notice it looks like that's not a stationary point of inflection. There was no intent to make that a stationary point of inflection. It's just going to be a shape that does something like that. So I'm not looking for perfect precision here. I just want you to be able to think through the shapes of what's happening. Okay. The second and final example here, let's have a look at same kind of idea here. So if we've got x to the power of 1/4 pictured here, so it's a sort of more extreme version of the square root graph. We want to then use that to sketch the graphs of x to the power of 3/4 and x to the power of 5/4. So we've got x to the power, y equals x to the quarter, and then if we raise that to a power of 3. Now you'll notice I haven't done 2/4, and that's because 2/4 would just be x to the power of a half. So the power always has to be in, which we already know would be, this less extreme version. So that would be y equals x to the power of 2/4, which would be x to the power of a half. We're already comfortable with that, so we'd simplify it down. So if we're going to take x to the power of a quarter and raise it to a power of 3, we're going to be cubing, okay? But we also want to remember that 3/4 is still a power smaller than 1. So if this is y equals x to the power of 1 here, okay, when we relatively speaking, if we raise a positive number to a smaller power than 1, it should still sit below 1, okay? Whereas if we raise, I didn't mean positive, I mean a number bigger than 1. If we raise a fractional value, so a number between 0 and 1, to a power that is smaller than 1, it's going to get smaller. It's certainly going to be smaller than the power of a quarter, because it's it's a bigger power than that. So if you raise a fraction to a bigger power, it gets smaller, but it's going to be bigger than x to the power of 1. Okay, so this should be our y equals x to the power of 3/4. The main difference that's going to happen with our y equals x to the power of a quarter and then to the power of 5 is that 5/4 is now bigger than 1. So the graph should be bigger than what x to the power of 1 here, and smaller than x to the power of 1 down here. Okay, so again, let's have a quick look at that. So let's put in the graph of x to the power of a quarter, which was the basic graph. And then comparatively, let's have a look at x to the power of 3/4. Okay, so that's what I've drawn as the blue graph, corresponds to the red graph on my CAS. And then if we have a look at, x to the power of 5/4, we should see that shift. So if I just actually let me just adjust my window all at once here, just so we can see what's happening a bit better. Let's just make that -3 and 3, and let's make that -3 and 3 as well. Okay, you can sort of see, if we put on the graph of y equals x, it should be right in between those two. We can see how the curvature of the 3/4 graph, which is the red graph, has changed to the power of 5/4 graph, which is the black graph that's now dipped underneath y equals x between 0 and 1, and then above y equals x when x is bigger than 1. Okay. Alright, so as I said, kind of lots to think about there. Please don't think that you're going to need to really do a lot with this. It's really just about you trying to be able to think through the logic of what the graph is going to look like. Set up a table of values if you need to. Sub in some values to plot some points to get a sense of what it looks like. Think about a similar graph and how does it compare to that. It's about using all of those different strategies to be able to think about what does this graph actually look like. And then obviously once we've got the basic graph, I could now ask you to draw the graph of y equals x to the power of 1/4 plus 1 by translating up 1. Or we could draw x minus 2 to the power of 1/4 by translating that graph to the right by 2, and all the different things we could do with the transformations. So there's a mixture of questions here to have a look at. Some are from exercise 1G, and there's also a couple of further questions to have a look at from exercise 7A, all around power functions. Use your CAS to help you if you need. I just want you to explore these different graph shapes.